Can you guys hear me? Can you guys hear me? Can you guys hear me? No, I don't hear you. You guys can hear me. So use the doc to write your questions. No, I don't hear you guys can hear me. So use the doc to write your questions. I just heard somebody's computer play back the broadcast. I just heard somebody's computer play back the broadcast.
So number 2 on the review sheet for magnetism, it is asking to do the F equals BIL sine theta. We strayed away from using the sine of theta in the equation or in class. So when you plug in your force, your magnetic field, your current, the length of the wire, and then the sine of 45 degrees.
Number 2 on the review sheet for magnetism, it is asking to do the F equals BIL sine theta. We strayed away from using the sine of theta in the equation in class. So you plug in your force, your magnetic field, your current, the length of the wire, and then the sine of 45 degrees.
All right, so number 2 on the electrostatics, it says rubbing the balloon on your head, and it has a charge of -2 microcoulombs. What's the charge on your hair? Because of conservation of energy, or excuse me, in this case, conservation of charge, the stuff that's left on your hair would be +2 microcoulombs. And part B, which has the excess electrons, your hair or the balloon?
Number 2 on the electrostatics.
For the electrons, it's the negative charge. So the excess electrons would go on the balloon, and your hair would be missing electrons. And then for part C, how many excess electrons? So here we have the 2 microcoulombs, so 2 times 10 to the -6 coulombs of charge. And then you need to know, and this is on the equation sheet, that you'll get was that remember, 1 electron has a charge of 1.6 times 10 to the -19th coulombs. So then when you figure that out, 2 times 10 to the -6th divided by 1.6 times 10 to the -19th. So you get 1.25 times 10 to the 13th. All right. Color subtraction of pigments color wheel, number 12. I can sure do that. So the color wheel for pigments, right? Get fancy here. I'm just going to use black and white. We have cyan is a primary pigment, right? We have magenta is a primary pigment, and we have yellow. So the primary pigments are exactly the same as the secondary colors for color addition. When you mix these, right, cyan is made up of blue and green. So blue-green. Magenta is blue-red. That's a B. Blue-red. Yellow is green and red. So when you mix them, the common color comes out. So when we mix cyan and magenta, the common color between these two is blue. So blue is right here. When we mix magenta and green, the common color is red. So then red comes here. And when we mix cyan and yellow, the common color is green. So green comes here. And then this, when you mix them all together, becomes black. Oh, the source of all magnetic domains. So that's the next one I see. It's an atomic structure. That's something that Mr. Rush, I know, asked during the magnetism unit. I'm going to tell you that that's not something you really need to know. So I'm going to put a line through that one here, if I can. Oh, look at fancy. All right, let's see. Next question. Can you explain how adding dots and X's makes something clockwise, counterclockwise? Sure can. All right, let's go back to here. So let's make this a little smaller. Okay, so remember, this is our key for right-hand rule for magnetism, clockwise, counterclockwise. So when we have this is counterclockwise current. Remember, this is the current that's being created. When we have a counterclockwise current being created, that produces a magnetic field out of the page, okay, a dot. When we have a clockwise current created, that produces a magnetic field into the page, okay? So here's an example. Let's say I have a bunch of magnetic fields into the page, like this. And we have a loop. And we're going to pull the loop out of the magnetic field. Okay, we're going to pull the loop out of the magnetic field. As we pull it out, we're losing, right? We're losing X's. So remember, we have to do the opposite of losing X's. We have to gain X's. You do the opposite of what you're doing. So we're losing X's. So as we pull this out, we need to gain X's. So this is going to create a clockwise current. Okay. Did that answer your question? I know that didn't help for the question answer for what MOPS would I suggest. Honestly, go through the review and I would just you're conceptually weakest at, because there's too many of them to go through. All right. So I'm here with the magnetism second number 3 here. A compass is just a magnet, right? It gets attracted to another magnet. And remember, it gets attracted to the north pole of the Earth, but it's really the Earth's magnetic south pole. Okay. Number 11 on electrostatics. Okay, so Coulomb's law. So I'll put that. This is Coulomb's law. The other number 3. Okay. All right, I'll come back to the magnetism one, the other number 3. Thanks for specifying there. Let me do the Coulomb's law one. All right, so Coulomb's law, F equals K Q1 Q2 over R squared. Okay, so we have a force of 25 newtons. K, remember, is a constant. You'll be given that. Again, you're going to get all the equations. You're going to get all the constants. So 9 times 10 to the 9th. 9 times 10 to the 9th. That's the 9 there. They're both the same charge. So I would write that as Q squared. And then they're 3 meters apart. So 3 squared, right? So then 9 times 25 is 225. So 225 equals this value here. It's going to come here. I'm not going to rewrite it like that. Times Q squared. So we're going to divide 225 by 9 times 10 to the 9th. And then take the square root of that once you get the answer. So you get 2.5 e to the 9th. E, remember, is times 10 too. It times 10 to the, negative 8 equals Q squared. And then take the square root of that. And you get 1.58 times 10 to the negative 4th. Coulombs. Okay. While we're doing this one, let me just go to number 12 real quick, because that's, again, more relationship questions, and we like to ask relationship questions. So, if we look at number 12, we have a force of 200 newtons, and we have 2 different values of Q, and we want to know what would happen if big Q were doubled. So we have big Q and little q, and they're a distance of just d apart. But we're not asking about changing distances. So these are just focusing on what happens to, actually part B is asking what happens to D. So question A wants to know what happens when we double Q, big Q, and triple little q. Well, if we double big Q and triple little q, this value is going to be 6 times greater. So nothing else changed. So my force is then going to be 6 times greater. So that would be 1,200 newtons. 1,200 newtons, right? For part B, it wants to know if we take and we reduce this to 1/4, the distance to 1/4. Well, again, it's 1 over r squared. So if we reduce by 1/4, we're going to increase the force by 1 over 1/4, and then square it. So that's going to be 16 times. So B is going to be 16 times 200. So we'll get 3,200 newtons. And then part C, if Q were cut into a third and Q were doubled and D were doubled. So here we got a couple of things to deal with here. If D's doubled, let's do that one first. If D is doubled, the force is going to go down by 4. So we're from 200 and we're going to divide that by 4. So we're at 200 divided by 4. We're at 50. That's the distance. That's taken care of. If little q were doubled, then this would double. So now we're at 100. And then if big Q were cut by a third, then this would be down a third. So overall, we'd have 33 newtons of force. That's the best way to do it. Break it up. All right, let's go back to the magnetism number 3, the other magnetism number 3. I guess there were 2 of them. Okay, the actual problem. All right, so a vertical wire, 55 centimeters long. So here's my wire, 55 centimeters long. Carries a current of 6 amps downward. So I is 6 amps. Experiences a force. There's a field into the page. So the B field is into the page. It's all over the place. So there's B fields all over, equal to 0.8 Teslas. The magnitude and the direction of the field. So we're dealing with a current of a length of wire. So this is going to be Bil. So just BIL, right? So 0.8 times 6 times 0.55. Don't forget to convert to, and we get 2.64. So the force is 2.64 newtons, right? Now we have to use the right-hand rule. The right-hand rule, right? So the magnetic field is into the page. Okay, so your finger is going to point into the page. Your thumb is going to point down the wire. Okay, so your finger is into the page. Your thumb is down the wire. And so where is your palm facing? Or if you're Mr. Rush's student, where is your middle finger pointing? And that's going to be pointing to the right. So that's the direction of the force. All right. So let's see. I think I am at I was here. Somebody, don't erase the questions though. Hello, whoever wrote Mr. Ravenscraft there. All right. Number 11 on magnetism. Did I do that one? I think I did that one. let's see, circuits 3A and B. Okay, so we're right here, circuits 3A and B right now. Would you be hurt if you fell from a building but arrested your fall by catching hold of a high voltage power line? And then would it make a difference until your feet touch the ground? So the answer to A is you wouldn't be hurt. At least not by the electricity. Because as long as you are only touching one wire, remember it's kind of like the demo where you put the hand on the Van de Graaff machine, you get the same voltage as the wire. So there's no difference of voltage, okay? But once it touches the ground, now you've given a path for the voltage to go, and then yikes. Yeah, then bad things happen because now you've given it a path. Okay, that's why. So you're okay as long as you don't touch anything else. But once you touch something else, then you're not okay. Let's see. AC versus DC. So everything that runs off a battery, uses direct current. Alternating current is what you plug into the wall. It's what we plugged into with the household electricity unit. Alternating current just means the electricity changes direction, where direct current is only one directional flow. Okay? So current changes direction in alternating current flows one direction. Direct current is what most everything we plug into the wall runs off of. Nice. Who put that there? All right, so I'm on waves number 16 and number 13. Okay, so let's go back to here. This is the one, this is actually a question a lot of you got wrong on the test, the beat frequency problem on the multiple choice. So the beat frequency is the difference, absolute value sign, the difference between the two frequencies. The difference between the two frequencies. So for number 16, it says if I have a 215 hertz frequency and a 217, then take the difference and we get 2 hertz. So that's the beat frequency. That's number FB right there. So that's number 16. The other one was, ooh, that was number 6. You wanted number 6. Okay, so number 6, I think we had a question like this on the test too. The bird watches a wave crest. And it says if 2 crests pass the pole each second, what's the speed of the wave? So they give you a picture like this. They say the distance between crest to crest is 1 meter. So remember, crest to crest, trough to trough, that is lambda. And so V equals lambda F. So the question is, how do we find F, right? It wants to know the wave speed. Well, if it takes 1 second for it to go through 1 cycle, then the period, and here's the answer for B too. The period is 1 second. But so that's period. So there's the answer for B. But remember, frequency and period are inverse of each other. So inverse of the period is the frequency. So on this one, if we take 1/1, we get 1. So we get V equals, and it's kind of silly, we get 1 meter times 1 hertz. So we get 1 meter per second. 1 meter per second. And then number 13. The idea of all objects have a natural frequency. Remember the making the wine glass vibrate. We had that glass in class. That's the best picture. I'm gonna draw all night right there. Or we had the singing bar, or the cardboard tubes. Those are natural frequencies. So if you can make an object vibrate at its natural frequency, you get that resonance, and that's when the things start to sing. All right, so we're moving on to number 7 here on electrostatics. How are we doing, everybody? Keeping up? Okay, let's go number 7, electrostatics. Actually, the very first thing that a lightning rod does is to try to draw a static charge from the air to stop lightning from happening. But if it doesn't, and clearly they don't all the time, it gives the lightning a direct path to the ground. So it doesn't catch any buildings on fire. Uh-oh, what just happened? What's next? Who put that in there? Nine through 14, huh? Okay, let's see. Let's start with number 13 on circuits. Seems what these might, let's see. $13. Okay, I'm going to pull up the review real quick. Oh, there I am. How lovely. I'm pulling up the review so I can show you and go through circuits number 13. All right. All right, so unfortunately I can't draw on this, so we can talk about what the answers are for this, and then if you have any questions, just write them in next to this one over here. So circuits number 13. For the following questions, assume all resistors have the same resistance. So which bulb in each circuit would have the most current? So the bulb, well, I guess we'll assume there is a bulb. Let's see. So we'll say the resistor. So which resistor in each circuit would have the most current? So if we go through here and we talk about the current, so for A, all of them have the same current. Okay, all of them have the same current because they're in series, right? In C, all of them have the same current because they're in parallel. Okay? Now, C's current is bigger. All right, I'm jumping ahead to letter C here, though. C's current is bigger because it has the least resistance because all three of them are in parallel. Remember, in parallel, resistance goes down. B, so if we follow the current, right, comes out of the battery, it comes here and it splits. And this branch right here has more resistance than this branch. So this resistor is going to get more current than these two resistors. And then here, the current's going to come here and split evenly because there's only two. And then it's going to come back together and all travel through this one here. So this resistor here will have the most current in it for D. Then going back to B, which circuit has the largest total resistance? The largest total resistance is in A because these directly add together. Those directly add together. So I hope that helped. Let's look at magnetism 9 through 14. Smiley face. All right, so 9 through 14. Number 9, right? An electric motor takes electrical energy and transforms it to mechanical. Number 10, the generator takes mechanical and transforms it to electrical. Number 11, explain in one sentence how an electromagnetic works, right? Coil of wire, current creates mag field, coil makes it bigger. There you go. You wrap a coil of wire around an iron nail or some metal, and you send a current through it, and the current creates the magnetic field, and the coil makes it, meaning the magnetic field, stronger or bigger. There is no 12, so 13, more coils or an iron core. You either add more coils or you add a bigger core, and definitely iron, and then it'll make it stronger. And then if you break a magnet in half, what happened? You just broke your magnet. You now have 2 magnets. All right, circuits 8, 9, and 10. Oh, let's see. Circuits 8, 9, and 10. Okay, so, well, there's no 10, so I'm a little confused on that one. But 8 and 9, right? The rules for series circuits, the rules are that current is the same, voltage adds, resistance adds directly. In parallel, voltage is the same, current adds, resistance adds inversely. I figured that, Maddie, that you meant 11. Number 11, they're wired in parallel. Measured in parallel because if something breaks in your house, it doesn't turn off the rest of the house.
Yeah.
All right, number 21 on light and color. Okay. All right, let's go through. We're right here, number 21 on light and color. Right? All right. Okay. So we're going to fill this in as we're just going to go across the chart here, and hopefully I'll talk you through it. Again, I can't edit, I can't write on this one, and I can't take a, maybe I can. No, I can't. I won't be able to paste this into the app, into the whiteboard. So let's talk about this real quick. Give me 1 second, please. I will be right back. Okay, I'm back. Sorry. Okay, so this line up here, everyone's still with me here, I hope. So the object, if we shine white light on it, this is what the object looks like. So in white light, which means this is what it truly looks like. It's red, green, magenta, cyan, and yellow. So if we take blue light and shine it on a red object, it's going to look black. Because remember, it's red because it only reflects red light. Same thing with green. Blue light on a green object, it's going to look black. Magenta is red and blue. So if we take blue light and shine it on something that's magenta, it's going to look blue because it reflects blue light. Cyan, blue and green, it will look blue. Yellow, red and green, it will look black. Okay. So we go through and you do the same thing for each of these, right? Cyan is made up of blue and green light. So if any of these on the top have blue or green or both, those are the colors that it's going to look like. So red is going to look black. Green is going to look green because of the cyan has green light in it. Magenta will look blue. Cyan will look cyan. And yellow will look green. Down to red. Red light, or excuse me, a red object in yellow light will look red because yellow light is red and green. Green will look green. Magenta will look red. Cyan will look green. And yellow will look yellow. Out of all of these, the only thing that would look, there's not there, if we had a blue object, that would look black. Okay. So remember, go through and in white light, this is the true color of the object right here. And then what color are we going to shine on it to what color it contains. If they don't match, then it looks black. For this one, is this number 9 for lights? Polarized versus unpolarized. Remember, polarized light is traveling a specific direction. then how can you tell if it's polarized? Polarized film or pair of polarized sunglasses, if you look through the light and you turn the film or the sunglasses and the light disappears and dims, then it's polarized light. A complex circuit, you're not going to have to do, because remember, we have a time constraint here. So, you know, the most that you're either going to have to do something like this, which is, again, parallel in series, or a series in parallel. We're not going to have you do anything more than that, just because for time. This is going to just show you, show us, if you use the VIR chart, right, show us that you understand the basic rules for series and parallel circuits, right? So I'll talk through it without actually going through the numbers. So remember your values for R1, R2, R3, your total goes here, and then these two here are in parallel, so you combine those in parallel. Those two are in series, so then you'd have your total. And remember, you'd be given a total voltage too. Down here, you do the series first, and then you do the parallel. Okay, same thing. You're going to give it voltage, find the current, total current. This is more something that we can go through in class tomorrow. I can easily do this on the board in a couple minutes for all the classes. So I'll leave it kind of at that. There are a ton of pen casts on the website for these. So again, make use of those. Go back and look at the series in parallel pen casts that we have on the website. Somebody answered that for me. Was that Mr. Strife? Yeah, there's no written portion. The test is 100 multiple choice questions. Electrostatics number 9 and 10. All right, so both of these are Coulomb's law. I gave you one already, Maddie. Shout out to Maddie. So Coulomb's law, F equals KQ1 Q2 over R squared. So I'll just do one of these. if you go back, if you logged on late, I solved one of these earlier. So after we get done, you can kind of go back and go through it. So number 9, find the force between 0.003 Coulomb charge and a 0.004 Coulomb charge by 1,000 meters. So F equals K, that's the value 9 times 10 to the 9th. That's the constant that'll be given to you. 0.003, 0.004, all over 1,000 meters squared. Oh no, my clan is being attacked. So 9 e to the 9, 0.003, 0.004. This is going to be really small. So 1.108 newtons. For number 10, you're just plugging in F instead and solving for R. Magnetism, second, number 1. So this one, this F equals BIL. Horizontal wire carries a current to the left. Magnetic field is directed down. So here's the current. Magnetic field is down. So again, just BIL. I'll let you guys do the math on that one. So this is number 1, magnetism, right? So 0.4 times 5 times 0.5, right? Well, I'll go ahead and do it. 0.4 times 5 times 0.5. So 1. So 1 Newton. And then the direction, again, right-hand rule. So your finger in the direction of B. So your finger or fingers, again, if you're Rush's class, it'd be your index finger. If you're in my class, it's your whole, all 4 of your fingers. Your thumb in the direction of I. So your fingers are down, your thumb is pointing to the left, and your palm is facing at your face. So force is out of the page. Force is out of the page. Okay. All right, number 19, sound. Let's keep it professional, people. All right, number 19. Calculate the sound wave frequency. So V equals lambda F. So we're trying to solve for F. V is 560. Wavelength is 6.6. Solve for F. So 84.8.
Chloe has some. She has some. Really?
All right. Waves number 9 and 21. 9 and 21. I'll just talk through the 9 and 21. I'll go to the picture and we'll run through it here. So remember, this is Doppler effect. As the car is moving toward observer B, right here on the right, the wavelengths are getting squished together. As they're getting squished together, the wavelength is shorter, so the frequency goes up. So behind the car, the wavelengths are getting longer, so the frequency goes down. If you looked above and below the car, the length really stays the same between the waves, so nothing happens vertically, it's left and right. So the observer at B, the frequency goes up. At A, the frequency goes down. The speed of the sound is not different. Moving doesn't change the speed of the sound wave, right? And then I answered the rest of 9. How does the wavelength change? Again, the wavelength is shorter. As you can see, the distances between the wave fronts here on the right, it's longer at point A on the left. Okay. Then the other one was number 21. So 21, again, beat frequencies. It's 386 hertz. If there's 5 beats, it's either plus or minus that. So you're either going 381. So either going 381 hertz or you're going 391 hertz, plus or minus 5. That's the beat frequency. Let's see. Sound 10 through 15. Let's see what those are. All right, so number 10, right? What must be present in order for a sound wave to travel? Okay, I'll get back to number 10. In order for sound to travel, you have to go through a medium. Number 11, through what type of material does sound travel fastest through? Solids. Number 12, the speed of sound when it's 55 degrees Celsius. So 331 meters per second at 0 degrees. It plus 0.6 meters per second per 1 degree C. So 55 degrees will add, if it's 0.6 meters per second for every 55, meters per second to 331. Hope that helped. 13, what is meant by, I covered that one earlier. 14, define resonance and give an example. So resonance is when an object vibrates at its natural frequency, and it builds up and it builds up and it builds up. So an example, again, the singing wine glasses, even your guitar, the body of the guitar resonating with the strings, so it's loud. All right, and 15, again, the beat frequency is the difference between two very, very similar but not exactly equal frequencies. All right, let me come back to number 20 here. Oh, 21. You're right, I did 20, not 21. No, I'll leave that there. 20. 21. All right, so number 21. Okay, so 21, we hear it's a sonar, it's an echo, but here's the key. It says time is 5 seconds. That's 5 seconds to go there and back. So one way, it's only 2.5 seconds. All right, so it gives us that it takes 5 seconds for the sound to go out and come back. So one way is 2.5 seconds. If we are using the fact that speed is 1450 meters per second, so velocity equals distance divided by time, right? 1450 equals then d divided by 2.5. So then d is equal to 3,625 meters. All right, let's see. Light number 3. So this is actually B, number 3. This is increasing frequency. A, you're welcome. All right, so I will be in all the physics classes tomorrow, going through any last minute questions you have. I hope you guys have a good night, and we will see you tomorrow.